Today, we are diving deep, literally into a force of nature so powerful it can reshape our world. We're talking about earthquakes. In the next few minutes, we're going to break down exactly what they are and what's really happening right under our feet. So let me ask you, have you ever felt it? That sudden, really weird shaking. Maybe it was just a little rattle, or maybe it was something way, way bigger. It's a crazy feeling, right? When the one thing you count on to be solid and still just isn't.
Well, that shaking is an earthquake, but while we're feeling it up here on the surface, the real story, the real action, is happening miles below us. So what in the world is going on down there that can cause all that chaos? Let's get into it. To really get what an earthquake is, you first have to understand the ground itself. And honestly, the best way to picture it is as a giant planet-sized jigsaw puzzle. That's exactly right. The Earth's crust isn't one solid shell like an egg. Nope. It's broken up into these massive, interlocking pieces. And if you can wrap your head around that one single idea, everything else about earthquakes is going to make so much sense.
So, how many pieces are in this puzzle? Well, scientists have mapped out about 20 major pieces, and they are always moving. I mean, it's super, super slow. They move at about the same speed your fingernails grow. So you'd never feel it, but trust me, they are constantly on the move. And these giant puzzle pieces, they have a name, of course. We call them tectonic plates. They're these huge slabs of rock that make up the whole outer layer of the planet, kind of floating on the hot, gooier layer just beneath them. Okay, so you've got these colossal plates, always drifting around, which brings us to the most important question. What happens when they run into each other, when they grind and bump and collide? And there it is. That's the whole secret. An earthquake is what happens when these tectonic plates interact. They can crash into each other, scrape alongside one another, or one can even dive underneath another. All of this friction builds up an absolutely incredible amount of stress and energy. Now, that exact surface where all this slipping and grinding is happening, that's called a fault plane. You can just call it a fault. Think of it as the literal crack between two of these gigantic plates, where all that pressure is building up. Eventually, all that stress has to go somewhere, right? When it finally breaks, it happens at one specific point, deep underground. That starting point, where the rock first slips and sends out all those energy waves, that's called the hypocenter. And that brings us to the word you've probably heard on the news a million times, the epicenter. The epicenter is just the spot on the map, the point on the Earth's surface that's sitting directly above the hypocenter. It's usually where the shaking is the strongest. Now, what's really fascinating is that how these plates bump into each other changes everything. It doesn't just decide what kind of earthquake we get, it literally shapes our world, creating everything from the highest mountains to the deepest oceans. Let's break down the three main ways they interact. First up, you've got a convergent boundary. This is where plates push directly into each other. That insane pressure can literally buckle the Earth's crust upwards and create enormous mountain ranges, like the Himalayas. Then you have a divergent boundary, where plates are pulling apart. As they separate, molten rock comes up from below and creates new ocean floor. And finally, there's a transform boundary. That's where plates slide horizontally right past each other. You know the famous San Andreas Fault in California? That is a classic transform boundary. So all this powerful movement releases just an incredible amount of energy. So how do scientists actually measure these things? And what are some of their biggest, most dramatic effects? The main tool in the earthquake scientist's toolbox is the seismograph. It's a super sensitive instrument that can detect the seismic waves, that's the energy, that earthquakes release. It lets scientists figure out how strong a quake was and pinpoint exactly where its epicenter was. And sometimes, the consequences of a quake are absolutely devastating. A perfect example is a tsunami. See, when a really powerful earthquake happens under the ocean, it can shove a huge amount of water upwards, creating these massive waves that can travel across entire oceans. So the ground beneath our feet is anything but static. It's this dynamic, constantly shifting jigsaw puzzle. The very same forces that can cause so much destruction are also the slow, steady architects of our planet, building mountains and creating new seas. It really leaves you with a mind-bending question. If this is what our planet looks like today, what do you think it's going to look like a million years from now?